Hi everyone, and welcome back to another episode of Science. In this episode, I'm going to be teaching you about the right-hand slap rule, which is one of three right-hand rules in our electromagnetism topic. One of them being the right-hand grip rule, the right-hand solenoid rule, and today, the right-hand slap rule. I'll also touch base on the right-hand grip rule today as well, but our main focus is the right-hand slap rule, which is what you see on my iPad screen here. So before I demonstrate it to you, let's go through what our right hand will be demonstrating. So if you take out your right hand and just have it in front of you and do it with me, in this right hand rule, your thumb is going to be the direction of the current. So the thumb is the direction of the current that will be traveling through the wire. Your fingers point in the direction of the magnetic field, and your palm is the direction of the force. So whichever way your palm is facing, that's the way that the force on the wire will be felt. So you'll find that the wire is being pushed in a particular direction once it's in a magnetic field. And I'll demonstrate to you what I mean by that in just a couple of moments. But take a few seconds here if you need to pause the video, have a look at this diagram and match it to your right hand. I want you to visualize your thumb representing the direction of the current, your fingers representing the direction of the magnetic field, and your palm will be the direction of the force. That's why it's called the right hand slap rule, because you slap with your palm essentially. And this can go anyway. You can go up, down like this, down like this, and up, left, right, like out of the page, into the page, all sorts of different directions. So practice just getting the hang of getting your right hand in the correct orientation to demonstrate the right hand slap rule. Okay, let's leave this to the side for just a moment while I demonstrate the next part of today's demo. Here I've got a couple of bar magnets, and I've just got a bit of blue tack and a piece of metal in between them to stop them from sticking to each other. I need a little bit of a distance between them. I've got my North Pole here and my South Pole here. So I might just mark it with a Sharpie as well. I'll put an S here. And my red is my North Pole. Grab my red Sharpie as well, and I'll put an N here for North Pole. Okay, so I've got here, I might just move my camera, my power box, and I've got it linked into the direct current terminals. I've got it on 2 volts just so it doesn't short circuit and turn off automatically too quickly. And I've got a piece of wire just hanging off a portable light here. But I want to be focusing on this wire in particular. Okay, so at the moment, I've got my magnetic field flowing north to south. Magnetic field always flows forth north to south. So your fingers should point in this direction, north to south. Now for the wire, I've got the current flowing up the wire in this direction. Okay, so your thumb is going upwards, or at least my thumb is going upwards on this wire. Now with my magnetic field facing this way, away from me, the current going up the wire, my palm is facing to the left of the camera. So I should feel a force that's going to push the wire to the left of the camera. And this is the force on the wire that I mentioned before. And this is the slap that I mentioned before. We should see the wire being pushed away from the magnet. So I'm just placing the wire inside the gap of the 2 bar magnets. Let's see if it gets pushed away. It does. It gets thrown out of that space between the magnets. I might turn it this way as well. And you can see it is really strongly repulsed. Now I can reverse this as well. If I change the direction of my field, so I'm flipping it over. So now I need to sort of twist my arm a bit here. So now the field is flowing in this direction towards the camera, north to south. The current is still running up the page, but look at the way my palm is facing this time. It's now slapping to the right of the camera. So I should see the wire go to the right of the camera, or in other words, be attracted to the space between the magnets. Let's give it a try. Place it there. And it is. You can see it's being really drawn quite strongly towards the magnet. And that's just on 2 volts. If I was to increase the voltage to 4 volts, the result would be even stronger. If I flip it again, it'll be repulsed even more strongly. The stronger the magnetic field, or the stronger the current that's flowing through the wire, then the stronger the results you'll get, the stronger the attraction or repulsion, depending on the direction of the magnetic field. Now you can also change the direction of the current to achieve an opposite reaction. So if I flip my field, so north to south, my fingers are facing in this direction and my thumb is facing upwards like this because the current is running up the wire in this case. I should get a force that's pushing the wire to the left, or slapping the wire to the left away from the magnets. Let's just test that again. It does. The wire is repulsed by the magnet. Now I'll leave my magnets in the same orientation, so the field always faces away from the camera, but I'll swap my terminals now so that I change the direction of my current. Bring the camera back here. So I'm keeping my magnet in the same orientation, but this time the current is running downwards. Before we had it running upwards, but now it's running downwards. The field is still going away from the camera, north to south, but my palm is now slapping to the right of the camera, or in other words, I should expect the wire to be attracted to the magnet. Let's try that. And it is. It's attracted to the magnet. If I swap the terminals again, just to really confirm what we're doing here, and bring the camera back. So my magnets remain in the same orientation. Field is facing away from the camera, flowing in this direction, but this time I've changed the current back to going upwards on the wire. So it should once again be repulsed by the magnets. Beautiful. Love demonstrating the right-hand rule. So you may be wondering, well, why is this the case? Well, it's also linked with the right-hand grip rule. So I'm just going to move the camera again to try to demonstrate. And let's see if I might weigh this wire down just to make it a bit more straight. Okay. See if I can get a good focus. All right. I've got my compass here. Before I show this, let's just double check that my compass is correctly orientated. So my south pole, which is the blue, is attracted to the red needle, which is the north pole for the compass. And if I bring it over this way, beautiful. The north pole of the permanent magnet, which is this red bar here, is attracting the south pole of the compass, which is the white needle. And we can have a bit of fun and just rotate it all the way around to see what happens here. So the white needle continues to be attracted until you get to the halfway mark, and then the compass is facing in this straight line like so, until it flips around to the other side, where the north pole of the compass is attracted to the south pole of the permanent magnet. Now we can keep going around. It flips over, south pole of the magnet the south pole of the compass is attracted to the north pole of this permanent magnet. It can get a bit confusing without practice. And once again, the halfway point has this orientation of the compass until we return to the south pole of the magnet, attracting the north pole needle of the compass. Now, because this magnetic field of the permanent magnet is so much stronger than the magnetic field of the compass, we can actually overpower the domains of the compass. So watch this. Right now, I've got my red needle attracting the south pole here. I can, just takes a few goes. Of course, now that I'm trying to demonstrate it, there we go. I've flipped the domains of the compass. Now I've got the south magnetic pole of the compass, the white needle, being attracted to the south pole of the permanent magnet, which doesn't really make sense. The reason why this is now possible is I've actually flipped the domains of the compass, so they're facing in the wrong direction in terms of what colors you want to mean the North Pole. We always want the red needle to be the North Pole, but in this instance, I've flipped the domain, so the white needle is the North Pole. So when you're working with your compass, always double check that your red needle is indeed the North Pole, and you can check it with the permanent magnet. You want the red needle to be attracted to the South Pole of the permanent magnet, and the white needle to be attracted to the North Pole of the permanent magnet. So I'm going to flip this back over. There we go. And now I've got the red needle, which is the North Pole of the compass, being attracted to the South Pole of the permanent magnet. And test this one. Beautiful. The white needle, which is the South magnetic pole of the compass, being attracted to the North Pole of the permanent magnet. Okay, now that we've confirmed that, let's touch base with our right hand grip rule. So I'll try to bring you right on top of the wire here. Let's see if I can get it to focus. All right. And I'll place my compass like so. Now, at the moment, I've got my current running up the wire towards the camera. The right hand grip rule, in this case, your fingers show the direction of the magnetic field. So the right hand grip rule has it wrapping around the wire in this orientation. So the magnetic field is running counterclockwise. Now I want my compass to line up with that field. So the red needle should always flow in the direction of the magnetic field. At the moment, the compass is facing down on the camera, but when I turn on the current, according to the right hand grip rule, it should flow in a counterclockwise. So the red needle should flip to the other side. Let's test that now. Look at that. And then I can wrap it around, and the red needle always follows. Well, let's try to get it in focus. Where's that focus point? There it is. The red needle always, and the power box short-circuited. Can I focus a bit higher? Yeah, let's bring it up here. Okay. Let's try again. There we go. The red needle always flows in the direction of the magnetic field. Of course, it doesn't last long. There's no load on this circuit, so the power box does short circuit. But the interaction between the field that is generated around the wire, due to the right hand grip rule, the magnetic field being generated as current flows through the wire, interacts with the magnetic field of the permanent magnets, the field that's running between these two poles. And I'm going to explain that link and why it produces a repulsive and an attractive force as soon as I'm done playing with this compass and this wire. So satisfying to do. If you ever get a chance, I would definitely recommend you also trying out these practicals as I'm showing you. Okay, let's come to the why the right hand slap rule occurs. Let me just grab my iPad once more. Okay, So we've got a simple diagram here that I'm going to help us interpret. Let's put this as portrait mode so we get more of the screen. Okay. So on the top here, I've got a north pole of a permanent magnet. And at the bottom of the screen, I've got a south pole of the permanent magnet. That means my field is running down the screen like so, north to south. And that's indicated by these red lines here. Now this blue circle in the middle, that's the wire. Because we've got a dot in the middle, that is the current running upwards, away from the screen, or out of the screen, or out of the page, it's sometimes referred to. According to the right-hand grip rule, that's going to produce a magnetic field that is running counterclockwise like so. Now, what does this mean in terms of the force that the wire is experiencing? Why does it get pushed out? Why does it get pushed towards the magnets? Let me explain that now. On this side of the wire, the field is running in the same direction as the permanent magnet. The field that is being produced by the current running through the wire, that's coming out of the page, is running parallel, or sorry, running in the same direction, I should say, of the permanent magnet field. So the field is strong on this side. If I look at this side of the diagram, the permanent magnet field is running north to south downwards on the screen like so, but the field that the wire is generating is actually running in the opposite direction. So it kind of has this cancelling out effect on the field. In other words, the magnetic field on this side of the wire is weaker, and the magnetic field on this side of the wire is stronger. Now, the result of this is that the wire experiences a force. I should use my right hand in this case. The force that the wire is experiencing is being pushed to the right of the screen like so. Let's look at a couple more examples. So here I've flipped the magnetic field. So now the force from the permanent magnet is going up the screen like so. So your fingers are running upwards like so. We've got an X here, an X shape for our wire, which means that the current is actually running into the page. So if I take out my right hand, I put my thumb into the screen, into the page, my fingers are going up the screen, and my palm is the direction of the force. So in this diagram, the wire is going to experience a force to the right of the screen. Now, as I'm doing this, I want you to practice as well. So for this one, I want you to just pause the video for a few seconds and try to orientate your right hand to the correct position, to the correct orientation that matches what this diagram shows you. So just pause it here. Okay, assuming you've paused it and you've had a go, now let me show you using my hand. So I've got the north and south here. So the permanent magnet's field is going up the screen like so. The wire here is a dot, which means the current is coming out of the page or out of the screen. Therefore, the force will be experienced in the direction that my palm is facing. So the slap is going to be left of the screen. Let's have one more go with this diagram. So just pause the video here for a few seconds and try to orientate your right hand in the correct position to match this diagram. Okay, assuming you've paused the video and have a go. Let me now show you what it should look like. So this time the north and the south, the field is running in this direction with your fingers. This X means that the current is running into the page. So, this is going to be a bit hard. I really got to twist my wrist and arm on this one. Current is going into the page, into the screen. Field is coming downwards. So therefore your slap is to the left of the screen like so. And from here, there's one more step, one more extension to what I'm teaching you, and that is a simple DC motor. So a simple electric DC motor uses these principles that I'm teaching you. Let's just fold this in half. So this is the most simple DC motor you can have. You essentially just have a single wire that is in a loop, and that wire is within a magnetic field. So I've got the north pole of a permanent magnet and the south pole of a permanent magnet. Now, when you run a current through this wire, the wire produces a magnetic field as well, according to the right-hand grip rule. In this case, the current here is represented by these arrows. So the current going through this wire is going up this direction. Now, the field is running north to south in this direction, shown by my fingers. The current, represented by my thumb, is going upwards along these arrows, up the page, and the field is going north to south, represented by my fingers here. So in this case, the force is going to be felt in a downwards direction on this wire here. It's a little bit tricky because I'm trying to demonstrate a three-dimensional model on a two-dimensional piece of paper. So if you can set this up in 3 dimensions using the materials, it is a bit easier to grasp because you can actually see the wire going in the direction of the force in 3 dimensions. Now, along this wire, the current is running to the right of the page. However, because this wire is running parallel to the magnetic field of these 2 magnets, this wire here actually doesn't experience a force. Any wire that is running parallel to the field does not experience a force. We're only looking at the wires that run perpendicular or 90 degrees to the field, which experiences a force. This one, the current is running down the page like so. Again, try to visualize it in 3 dimensions. So in this case, I've got my field running north to south in this direction, and the current is flowing down the page, which is the direction of my thumb. So for this one, we're producing a force that's going up towards the camera. Or in other words, that's going to produce a force that pushes this wire upwards. The result of these 2 forces is that it gets the motor spinning. That's how DC electric motors spin. That's how they turn. You're essentially working with the force, the magnetic field that is produced on the wire by a current running through it, as well as some permanent magnets on either side of the motor. And that produces a turning rotation, a turning movement. There's a couple more diagrams that I want to go through as well, because they do come in a variety of diagram shapes and pictures. So I just want to make sure I cover a couple of different examples with you. So this diagram looks a little bit more complicated, but it's actually showing the same thing. It's just showing a bit more information. So let's start with the direction of the current. We've got a positive here and a negative here. That means the current is running in this direction, positive to negative. Sometimes it's also represented by a big line like this, which is the positive, and the smaller line is the negative. So if I follow that here, the current is running along this wire in this direction, like so. This time my north is flowing into this south here, so my field is going in this direction. Now, the current is running up here, so my thumb needs to point this way along the direction of the current. My fingers need to point in the direction of the magnetic field, and that produces a force coming up towards the camera. In the context of this diagram, that's going to produce, maybe I'll do this in thicker pen. That's going to produce a force that goes up like so. And the diagram for it is just here. If I come to the other end, the current is running down like so, back through the brushes. So my current is flowing in this direction, shown by my thumb. The field is running in this direction, shown by my fingers. This time I'm slapping downwards, and that's going to produce a force going down on the motor. So this motor is spinning in a clockwise direction, like so. I think I had one more on this side as well. I did. Let's just fold my paper once more. Okay, so here we don't have a positive or negative. We've just got these big lines and little lines, big lines, little lines. So in this case, because we've got a big line here and a small line here, this is my positive here, this is my negative here. The current is running in this direction. And there are some arrows here on the diagram too. So we're running like this. There's no force on this wire because it's parallel to the field. And we're running this way. So let's do this as well. Whoops. Oh, nearly a disaster. Okay. My thumb, I've got to twist my arm a bit here, is trying to be in line with those arrows there. My fingers are running north to south like so, and that's going to produce a force, a slap that's going upwards. And the diagram shows that force here. If I go the other way now, so my fingers are running north to south, my thumb is representing the direction of the current, that's going to slap down the page in this manner. So that's going to get the motor turning in a clockwise direction. Okay, and that was everything I wanted to cover for the right hand slap rule. If you've got any questions at all, please do ask them in the comments down below. Or if you want me to extend the video in any way or make a video on anything particular, also write me a comment. Otherwise, thank you for joining me on this episode of Science. Smash the like button, hit subscribe, and I'll see you in the next one.